Good afternoon, everyone. I'll be talking about NicPic, scalable and accurate end-host rate limiting. So this is joint work with my colleagues Vimal, Abdul, George, and Amin spread across UC San Diego, Stanford, and Google. So over the last 5 to 10 years, we've seen the rise of several different cloud services, such as Amazon Web Services, Windows Azure, Google App Engine, etc. So with such cloud data centers, essentially you have a lot of different services or tenants that are sharing the physical infrastructure. For example, you might have virtual machines of a few different tenants or different services like Reddit, Instagram, and Netflix, which are essentially running on the same physical server. So what are the trends that we see in the infrastructure hosting these different services or cloud services? So the processors have become beefier over time, and we have more cores in each CPU. And servers also typically have multiple sockets these days, with 2 to 4 socket configurations pretty common. And we can easily pack tens of cores on a single physical server. So memory has become cheaper and denser, and we can place about 100 gigabytes of memory on a single server. With networking, we're able, 10 gigabit Ethernet is pretty much commodity today, and 40 gigabit Ethernet is pretty much just around the corner, and people are already thinking about deploying 40 gigabit solutions. Similarly, disks or storage has also become cheaper and denser, and we can easily pack tens of terabytes of storage on any single physical server. So all of these trends essentially mean that we're able to build denser compute clusters, and the virtual machine density, or the number of virtual machines that you pack on any individual server, has been increasing. So when you're sharing physical infrastructure between many different tenants or services, this makes resource management and allocation very important. And over the last several years, we've developed a lot of good techniques for virtualizing or sharing the CPU, memory, and storage, such as time sharing, or essentially carving out separate chunks, or essentially dedicating cores or portions of memory for different services. But what about network virtualization? So on the one hand, we have some techniques like VLANs or access control lists in switches, which essentially provide security. So you can isolate the traffic and exactly specify which virtual machines can talk to which virtual machines. But what about performance guarantees, network performance guarantees, and isolation? So that is something that we're still trying to solve today. And as you can imagine, there have been a number of different proposals in this space for essentially performing network resource allocation. So in the bandwidth management space, you have proposals like Octopus, Seawall, IQ, etc., which essentially try to provide bandwidth isolation and performance guarantees to each tenant in the data center. Similarly, congestion control presents challenges of its own in the data center due to the unique characteristics of data center networks, such as having very high bandwidth and low latency coupled with pretty bursty traffic. So again, there have been a number of different proposals for congestion control in data centers. So across all of these different solutions, one thing that we see to be common is that they all rely on an underlying substrate or a fundamental primitive of programmable rate limiters. So a natural question to ask is how many rate limiters are actually needed? So how many rate limiters do you need on an individual server? So congestion control is typically done on a per flow basis, which means that you need about as many rate limiters as you have number of flows on the server. But what about bandwidth management? Well, let's take an example. So suppose you have a few different tenants in the data center. Each of them is allocated some number of virtual machines, and these virtual machines are connected by a network or of a certain virtual link capacity. So all these virtual machines are essentially placed on some physical servers, such as that's shown here. So now, essentially, you want to reserve or allocate bandwidth for each tenant on the different network links that they're sharing. So, and all these reservations or rate limits are essentially enforced at the end hosts. So let's see how this is done. So clearly, you need at least one rate limiter for every virtual machine or tenant that is placed on a single server. So this is to isolate the two tenants or multiple tenants that are sharing that server's access link. But is that sufficient? Well, what if you have multiple source virtual machines that are sending traffic to the same destination? So in this case, if you were to just rate limit each source virtual machine to the total access link capacity that's required for that's allocated to that virtual machine, you might end up oversubscribing the destination. So this is clearly a violation of the reserved capacity at the destination. And the way to address this is to essentially rate limit every pair of communicating virtual machines. So for every virtual machine that's communicating with the destination, you want to rate limit them individually. So for example, VM1 to VM4 traffic is rate limited separately from VM2 to VM4. And every destination that a source speaks to is rate limited individually. In fact, this is exactly what is done by all these different proposals like Octopus, Seawall, IQ, Gatekeeper, etc. So now that we've seen that you need to rate limit every pair of communicating virtual machines, let's come back to the question of how many rate limiters we actually need. So let's perform a simple back-of-the-envelope calculation. So suppose you have about 20 virtual machines on a physical server. Well, this is a pretty reasonable number, and in fact, it's quite conservative considering that the virtual machine density is increasing, and we're able to have several cores on any individual server. And now if each virtual machine has 50 peers that it is communicating with, so there are 50 destinations that it's sending traffic to, or about 50 flows that are originating in that virtual machine, then you need about 2,500 rate limiters. Well, this was a simple back-of-the-envelope calculation, but the key takeaway is that you need to have thousands of rate limiters or any individual physical server. So now that we've established you need a lot of rate limiters, so what support do we have on end hosts for rate limiting traffic? So on the one hand, you have support from the operating systems. For example, the Linux QDisc or the queuing discipline layer allows you to rate limit individual traffic classes. On the other hand, you also have support from some NICs, which can actually support native rate limiting in the hardware itself. So what are the pros and cons of these two approaches? So the software approach can really scale to a lot of classes. You can essentially store information, store packets for each individual traffic class in the host memory, which is managed by the operating system. On the other hand, the software-based approach does not really work very well at high link speeds. And this is particularly a concern as we are moving to 10 gigabit Ethernet and beyond. And the other downside of the software approach is that it has pretty high CPU overhead. So there's a lot of interrupts that the software has to deal with, essentially performing all the scheduling for different traffic classes, etc. The other downside of the software approach is it's not very accurate or precise. The rate enforcement itself can be pretty bursty. So the other researchers have shown that it is desirable to have very well-paced traffic that is going out onto the wire, such as in the Hull project, which was at NSDI last year. So on the other hand, if we look at the hardware-based approach, it works really well at high link speeds, and it has very low CPU overhead because all the scheduling tasks are offloaded to the hardware. And it's also very accurate and precise. So the hardware is really good at performing very fine-grained timing operations, etc. However, the downside is that this doesn't scale to support a lot of traffic classes. So the NICs today typically support on the order of about 8 to 32 traffic classes that can be individually rate limited. So this is clearly about 2 orders of magnitude less than what we actually need on the physical servers. So with NicPic, we wanted to design a system that can scale to a lot of traffic classes while still having all the benefits of other hardware-based approaches. So NicPic is a NIC design which natively supports rate limiting for thousands of traffic classes in the hardware. And we believe that this can be achieved by a reorganization of some of the responsibilities of the NIC and the operating system. So if you see the NIC and the operating system, they store packets, store different information about different traffic classes, and they perform different tasks like scheduling and things like control plane activities. And we believe a simple reorganization of the responsibilities can actually help us achieve the goal. So now let's start taking a look at how we are actually going to achieve this with the NicPic design. So we'll begin by taking a look at the transmit path in today's servers. So this picture essentially represents a modern state-of-the-art server where you have a pretty modern NIC, which actually supports multiple transmit queues that can be individually rate limited in the NIC itself. And you have some number of queuing discipline queues which are maintained by the operating system in host memory. So the way the transmit path works is when the operating system finds that a packet needs to be transmitted, it essentially notifies the NIC about this packet that has to be transmitted. The NIC then DMAs or pulls this packet from host memory to its own internal NIC transmit ring buffer. Subsequently, it schedules the traffic from these different ring buffers that are on the NIC. So it has, let's say it has about 32 queues. So it's going to figure out which is the next packet that has to be transmitted from among the ones stored in these 32 queues, and then eventually transmit the packet out onto the wire. So as you can observe, the key characteristic here of the NIC is that it follows a pull and schedule design. So it first pulls the packets from host memory to its internal buffers, and then schedules traffic from among its internal ring buffers. So now let's take a look at what the NIC and the operating system are actually good at doing. So the NIC, on the one hand, is really good at doing very fine-grained per-packet operations. So it can maintain fine-grained timers, do things like scheduling, and it's also good for offloading all real-time operations from the CPU to the NIC. Right? So it's very good at doing fine-grained pacing, for example. It's also good for things like computing checksums, transmit segmentation offload, things like that. On the other hand, the operating system today is really good at managing a lot of state. Essentially, it can store separate queues in the host memory. It can have essentially store the packets separately for each individual class and manage all the state in the host memory. So it's also good for performing traffic classification and all sort of control plane activities, such as configuring rate limits or weights for different traffic classes, configuring which virtual machines can have access to which queues, etc. So with NicPic, we want to essentially exploit all these different capabilities of the NIC and the operating system, and essentially use these different capabilities to achieve our goal. So the first key idea in NicPic is to use the host memory for storing the per traffic class queues. So the host memory, or DRAM, is essentially cheap and abundant, especially on servers. On the other hand, NIC memory, or SRAM, is typically very expensive and pretty limited. So the NICs have much lesser memory, and typically you can't store individual traffic queues on the NIC. So if you want to support thousands of traffic classes and separate queues for each of these classes, you can't really afford to store all those packets on the NIC. And the way we're going to do this is essentially leverage the host memory for storing the packets. So the packets are in the host memory to begin with. So we're just going to have per class queues. Essentially, for each class, we have a separate transmit queue that is stored in the host memory itself. And the NIC just stores some metadata about all these different queues. So for example, it'll have pointers to these different queues. It needs to store the weights or rate limits for each of these queues, for each traffic class. And essentially, it needs all this information for scheduling. So this is the key aspect which allows NicPic to achieve scalability to thousands of classes. So since we are storing all the different per class queues in host memory, we're able to support thousands of queues. So the next key idea in NicPic is that we perform all the real-time scheduling on the NIC. So like I mentioned before, the NIC is really good at maintaining fine-grained timers, acting on performing all real-time or per-packet operations. Right? So we're essentially going to have the NIC compute all the scheduling. We essentially take care of all the scheduling on the host. So the NIC knows the rate limits for each of these classes, and it has the metadata stored on the NIC itself, as it's pretty small in size. And it's going to use this metadata to compute the schedule. And then once it figures out the order and the timing in which packets have to be transmitted, it's going to pull or DMA these packets on demand from the host memory for transmission. So all the control plane activities, like setting different rate limits, configuring traffic classes, etc., can be handled by the CPU. And the CPU in this case is also free to batch up network processing. It can essentially enqueue packets in bursts and let the NIC actually handle the actual fine-grained scheduling of these individual traffic queues in this case. So in this way, the CPU overhead is substantially reduced without giving up any of the precision, so that you can still achieve very well-paced traffic on the actual wire. So this is a diagrammatic representation of the proposed NIC design. So here, as you can observe, all the per class traffic queues are maintained in host memory. So the NIC just has a scheduler. So it doesn't have separate queues for each traffic class. So in this case, again, whenever the operating system enqueues a packet into one of these queues, it's going to notify the NIC saying, here's a queue that has a packet that can be transmitted. So the NIC first schedules all these classes per class queues that are stored in host memory. And only after scheduling does it pull or DMA the packet from the host memory to a small NIC buffer from which it's actually transmitted out onto the wire. So the key differentiator in this design is that the NIC has a schedule and pull design. So it first schedules these different traffic classes and then pulls the packets from host memory on demand for transmission. So what kind of performance can we expect if we build such a NIC? So we wanted to measure the CPU overhead and the accuracy of different approaches. So we looked at Linux hierarchical token buckets, or essentially the software-based approach, and a hardware approach using the Intel NIC-based hardware rate limiting. So we had a UDP load generator generating MTU-sized frames, MTU-sized packets, and this was run on a 16-threaded machine. Essentially, we had 16 parallel instances of the UDP load generator generating traffic to a number of different traffic classes. And since we don't actually have a NIC which implements such scalable rate limiting, what we did was essentially extrapolate the hardware rate limiting that is offered by the Intel-based NIC, so which offers a few limited classes. And we essentially tried to, for this very specific workload, we were actually able to just multiplex multiple transmit classes onto the few transmit queues that were actually available. So these different graphs show the actual CPU utilization and burstiness that we observed under different scenarios. Let's take a look at them scenario by scenario. So in the first case, we ran a bunch of experiments where the total configured rate limit was 1 Gbps, and we essentially varied the number of total traffic classes, and with an equal rate limit for each traffic class. So in this case, we observed that the CPU utilization was pretty low, both for the software approach and a hardware approach like NicPic. And the same is the case for the burstiness as well. The burstiness is again comparable both for the software and hardware-based approaches. So essentially, at 1 Gbps, both the software and hardware approaches are both acceptable. So let's see what happens at 5 Gbps. So in this case, the green bars represent the software-based rate limiting. So as you can see, the CPU overhead or the CPU utilization with the software-based approach is nearly 4 to 5 times as much as the CPU utilization with this hardware-based approach, such as you could achieve with NicPic. So, and the blue and white bars essentially represent hardware rate limiting and the extrapolated hardware-based rate limiting. So similarly, when it comes to burstiness, since the operating system batches up transfers to the NIC, we observe that the burstiness is significantly higher with the software-based approach. And essentially, the NIC or the hardware-based approach can achieve significantly lower CPU utilization and burstiness compared to the software approach. And when we further increase the total rate limit to 9 Gbps, so we observed that the hierarchical token buckets or the software approach essentially could not keep up. It could not even achieve more than 6 to 7 gigabits per second of throughput. So those bars are actually not pictured here, as it could not even achieve the rate limit that was configured. On the other hand, we observed that the hardware-based approach was perfectly capable of keeping up with the line rate and achieving 9 gigabits per second. And as you can see here, both the CPU utilization and burstiness are pretty low. So now that we have seen the NicPic design, and we've also seen that the performance is very promising, so what are the implications of such a design? So on the one hand, it's a very scalable design. So in theory, you could possibly rate limit every single flow on the host. And so if you have thousands of flows that are originating from a single server, you could actually rate limit each and every one of those flows. So the rate limiting is also very accurate, and you can in fact achieve near perfect packet pacing as all the rate limiting is done by the hardware. So this could in theory help us achieve very ultra low buffer occupancy in switches and operate the network with very low levels of internal congestion. So in fact, this was an approach that was studied in the Hull paper in NSDI last year. Further, the fact that we are doing all the rate limiting in the NIC directly, and since the hardware is taking care of all rate limiting, we can take advantage of features like SRIOV and kernel bypass or hypervisor bypass, thereby exposing the NIC directly into the virtual machine. And this would reduce latency on the transmit path on the servers. With that, I'd like to conclude. So we saw NicPic, which is essentially a scalable NIC design for rate limiting thousands of traffic classes directly in the NIC. It is able to perform this with very low CPU overhead and also offers precise rate enforcement. Thank you, and I'll be able to take any questions now.
What's the difference from your work and the TC in Linux? The TC as a chapter controller, it seems to have similar. Okay, you can please repeat the question.
Sure. So the question is basically what's the difference between what is offered by Linux TC versus our approach. So the Linux TC approach that you ask about is exactly the software-based approach that we explored here. So hierarchical token buckets, or Linux hierarchical token buckets, are configured using TC. So the software approach essentially has very high CPU overhead, and the operating system is essentially batching up transfers. On the other hand, if you perform the rate limiting natively in the NIC, the hardware is able to offload all the scheduling responsibilities, thereby reducing CPU utilization.
So your work is only work for the Intel 8 to...
No, it has nothing. So we just use that for our prototype. But
other NIC don't have the offloading for the rate limiting?
They don't today, yes. So we are essentially proposing a NIC design which would enable scalable rate limiting in the hardware.
Intel 8 to 599, how many rates, how many flows they can...
So they can rate limit on the order, a few tens of different queues. So in our setup, it was able to configure about 16 different queues, so one for each core. So with virtualization and SRIOV support, you could extend it up to 128. So that's the maximum that they support in the Intel NIC.
Okay, but I have one more. How is accurate for the Intel 8 to 599 the timer resolution?
So the measurements that we had for the hardware rate limiting are actually with the Intel NIC. And we don't know the internals of how they actually perform the rate limiting. But our observation has been that they have a granularity of about 2 packets, a burst of at most 2 packets from each queue at a time. Yeah.
Hey, I think that's actually a very interesting idea. I'm kind of wondering about the hardware design application of this thing, where today you already have some software rings, obviously, where the ownership is shared between the CPU and actually the NIC, and then, as you said, transfer with DMA from its internal hardware, RAM. Now, if you go with this design, it means like, what does that mean for the hardware? Because effectively, the SRAM, like you said, doesn't seem to be necessary no more. And I'm wondering, like, why they didn't go in that direction in the first place? Why they needed this SRAM, and what makes you think now it's not necessary no more?
Right. So let me clarify a little bit there. So the SRAM is still required. Okay. So one, you have some amount of metadata that has to be stored, which is stored on the SRAM. And 2, you still need a small FIFO. You just need one small FIFO of, say, 10 packets that you still need to maintain on the NIC to keep the link busy. So, I mean, the advantage of having buffering is so that you can keep the link busy, right? And the way the NICs have evolved is you basically had a single queue NIC, and over time you needed some basic support for prioritization, and then you needed support for essentially having different CPUs enqueue without serialization with a shared lock. So for that, you had multiple queues in the NIC, and that's how we evolved from a single queue NIC to a multi-queue NIC. And that is basically the support that you have today in NICs. And basically, we are proposing a design where you can actually scale to a lot of classes, which is the need today in virtualized data centers.
Is there any latency issues with the design that you have?
So we don't expect any latency issues in terms of, for example, increasing the latency on the transmit path itself. But the kind of latency that we are concerned about is, so one of the challenges is going to be, what is the rate limiting algorithm? What is the scheduling algorithm that you're going to implement on the NIC? So can it keep up? And we do have some ideas, and there are obviously several rate limiting algorithms or scheduling algorithms such as DRR, which can scale to essentially support a lot of queues. And one of the challenges is, since you're pulling in the packets on demand, so even today, the NIC does DMA packets, but we are changing the order. We are first scheduling and then pulling in. So we need to compute the schedule a few packets ahead of time. So say about 10 packets, 15 packets. So we are still trying to explore and exactly evaluate how many
DMA requests you need to pipeline ahead of time.
So
classes and rate limiters? How are you mapping them?
Our claim is you don't have more classes than number of rate limiters. So you can essentially support a separate class or a separate queue for every single class that you want to rate limit.
Maybe I'm missing the terminology. You said you wanted a rate limiter for VM pair.
Yes.
And your NIC had 16 rate limiters.
Yes. So the NIC that we used was basically, so that's not the NicPic design, right? So this is basically a commercial NIC that's available today. So what we are proposing is basically, so we just used this NIC for evaluating our proposed design, and we extrapolated what we could do in theory if hardware was actually scalable to thousands of rate limiters.
Right. But then how much your NIC cost?
So we believe that the cost, I mean, of course, I'm not a NIC vendor, so I can't speak about the cost of the NIC itself directly, but we believe that trading off some of the buffer space, rather than using it for storing packets, if you just need it for metadata, the actual amount of silicon that you need is, so the NICs, for example, already have schedulers. So you need a more scalable or a different scheduling algorithm, and they already perform DMA. So in a sense, you're just reordering things in the pipeline.
Did you ever consider buffering the packets, actually implementing the physical queues on the NIC itself? I mean, you said earlier in your talk that NICs only have SRAMs, but there are other hardware platforms, programmable hardware platforms that provide you with sufficient storage density on the NIC itself. Does that give you an advantage?
So from our experience and whatever limited discussions we've had with NIC vendors and few other people, it is our belief that the NICs which actually can support a lot of buffering on the NIC in SRAM, so not DRAM, would actually cost significantly higher. So if you use DRAM, on the other hand, the cost would be lower. However, the latency would increase on the transmit part.
Yeah, no, I'm not talking about standard NICs because you're absolutely right.
Yeah.
Only SRAM and that would be expensive. But
So we still want a design for data centers that can be a commodity NIC, which wouldn't be significantly more expensive. Yeah.
I have the same latency. Please.
Have you looked into DDIO technology, how this affects or actually improves the technology? The DDIO, I mean the technology, the Intel technology that can push data directly into the cache of the processor, of the CPU processor, which actually improves the performance and the processor doesn't need to go to zero.
So one thing is, on the receive side, DDIO can completely be used as it is today. We change nothing on the receive side. On the transmit side, we would not necessarily be able to use DDIO directly because we're essentially relying on the NIC performing the DMA transfers. So one option to essentially enable both, essentially having very low latency using DDIO as well as having rate limiting support, is to have a few queues for which you have DDIO, and those are natively rate limited in the hardware with a small amount of buffers as it is today. But for all the other queues, you can essentially use this approach.
One more question. Is this NIC design also good for non-data center usage?
This design is perfectly capable of being used in other applications as well. So if you want to use just rate limiters, if you want to have support for a lot of rate limiters, you can essentially use this design. And it's not all that different from current NICs. They already have a lot of the components that we need, except not arranged in the fashion that we need.